Now, after having understanding of importance of quantum mechanics, let us now come to the second part of our lecture, the fundamental principles the quantum mechanics is based upon. Three fundamental pillars of quantum mechanics are the dual nature of matter given by de Broglie, Heisenberg's uncertainty principle, and the Schrödinger equation. In classical mechanics, a particle and a wave are two different entities, or these are two unrelated concepts. Whereas in quantum mechanics, there is nothing which has property of only particle or only wave. De Broglie proposed that the particle with momentum p have a wave nature and can be represented by a matter wave of wavelength h divided by its momentum. Let us take two examples of light photon and electron to understand it. A photon shows wave-like nature when we think of interference and diffraction, and this same light photon behaves like a particle for photoelectric effect and Compton effect. On the other hand, wave nature of electron is shown by the Davison-Germer experiment. The de Broglie wave is also known as matter wave. Now, in order to derive the result of de Broglie, let us take an example of photon again. Its energy is given by h nu and mc square by its wave nature and particle nature respectively. So this is by wave nature or Planck's hypothesis, and this is by the particle nature of photon. Since both are the energies of same photon, on equating these, this gives result lambda equal to h upon p. Let us get acquainted with the estimates of the order of de Broglie wavelength. For this, let us take first example of cricket ball. If we put all the values of its mass and typical velocity, then lambda or de Broglie wavelength for the cricket ball comes out to be of the order of 10 to the power minus 34 meter, while de Broglie wavelength for an electron accelerated by a 1 volt potential is 1.2 nanometer. So there is a huge difference between these two wavelengths. Here we see that the de Broglie wavelength of a cricket ball is negligible.
So one can say that quantum mechanics is not required to understand motion of cricket ball, whereas quantum mechanics is essential for the understanding of motion of electrons.
Let us derive the expression for de Broglie wavelength of an accelerating electron, and for this we will take its energy if it is in a potential V. The kinetic energy of an electron in potential V is EV, and this can give the momentum of electron in terms of the potential, and this momentum can give directly the wavelength of matter wave, and this is h divided by under root of 2 MeV, where E is electronic charge and m is its mass. If we put all the values of mass of electron, charge of electron and Planck's constant, then it comes out to be lambda equal to 1.228 over under root of V nanometer. So this is the formula for de Broglie wavelength of an accelerating electron in a potential V. But it is valid only for slow moving electron. And what if the electron is moving relativistically? When a particle of rest mass m0 moves with velocity v, which is comparable with the velocity of light in vacuum,
V comparable to c means velocity greater than or equal to half of the speed of light,
then its mass increases with this formula. So if electron has a rest mass of m0, which is equal to 9.1 into 10 to the power minus 31 kilogram, then the mass of electron will increase if its velocity increases. So mass of a relativistically moving electron will always be greater than its rest mass. So there should be a correction in the de Broglie wavelength of the electron. To find that correction, we need to have a factor by which the wavelength is increased, and that factor should be in terms of the known parameters like potential. To find that, let us have this approach? mc square is the energy of a particle in motion, and the total energy of particle in motion is the summation of kinetic energy and potential energy, while m naught c square is its total energy when the particle is in rest. So m naught c square must be its potential energy only. So the difference between these two can give the kinetic energy like this, and this formula can give the expression of mass m in terms of v, e and m naught like this. So all we need to do now is to put this expression in formula for de Broglie wavelength, and it comes out to be this. Now if you put the values of h, e and m naught, then we get the corrected formula for de Broglie wavelength of an accelerating electron in potential V. There are few estimates of de Broglie wavelength. The de Broglie wavelength of an electron moving with 1% velocity of light in vacuum is 2.4 angstrom, while the same for an electron moving in influence of 100 volt is 1.22 angstrom. These are properties of de Broglie waves, like de Broglie wavelength is shorter for larger mass particle. The de Broglie waves are pilot waves, means these waves guide a particle, and vice versa also, because de Broglie waves represent a particle. If there is no particle, there will be no wave. So these waves run in the same direction in which a particle is running. Next, the de Broglie waves are neither mechanical wave nor these are the electromagnetic wave. These are a third type of wave known as matter wave, and these are not the wave actually. So these cannot be observed because this is the wave model to describe and study the matter behavior. Again, the de Broglie waves are the probability waves. It means the amplitude of wave reveals the information of probability of finding a particle in space. A large wave amplitude means a large probability of finding the particle. The matter waves consists of a group of waves. It means a particle is not represented by a single de Broglie wave. It is represented by a number of waves. Why? We will discuss in next slides. After de Broglie hypothesis, let us talk about Heisenberg's uncertainty principle. According to Heisenberg's uncertainty principle, it is impossible to measure position and momentum of a particle simultaneously with absolute accuracy. It means if there are uncertainties in measurement of position and momentum equal to delta x and delta px, then the product of these two cannot be less than h bar. And this is also true for delta E and delta T, where delta E is uncertainty in energy and delta T is uncertainty in time. It is important to note here that the uncertainty principle is valid only for uncertainty in position measurement along x-axis and momentum measurement along x-axis. If we measure the momentum along y-axis and position along x-axis, then the product of uncertainties can have any value. It may be less than h bar. So there are only few pairs for which the uncertainty principle holds. Those pairs are known as conjugate pairs, and these are px and x, y and py, z and pz, and time and energy. These are few predictions by uncertainty principle. Heisenberg's uncertainty principle proves that the free electrons cannot exist in nucleus. The energy levels of an atom are of finite width. The energy level works as metastable state if its width is small. The atomic simple harmonic oscillators cannot have zero ground state energy, and it gives the correct estimate of radius of Bohr's first orbit. If the results of uncertainty principle and matter wave are matched with each other, then there come some implications. The problem is we cannot find the exact de Broglie wavelength of a particle because we cannot find the exact momentum of the particle. Therefore, the velocity of particle will be different than that of individual wave representing it. So if we have the equation of matter wave like y equal to a sine omega t minus x upon v, where omega is angular velocity of vibrating particles and v is the wave velocity, or this k is wave propagation vector, then this angle or this are known as phase angle. The velocity of a wave can be defined as the velocity of a point on a wave, the phase of which is not changing with the time, like this. So if phase is not changing with the time, then differentiation of the phase angle with respect to time should be 0. And this gives the velocity of a wave is equal to v or omega by k. dx over dt is the velocity of the wave. Because this is defined as the velocity of constant phase point on the wave, this is known as phase velocity of the wave, and it is represented by Vp. So Vp is omega over k. Now, what about the velocity of a particle? Because a particle cannot be represented by a single wave. So, suppose these are two waves the particle is represented by. This is the central wave, and the another wave is differed by the first wave by only small quantities of omega and k, that is omega plus delta omega and k plus delta k. So these two waves are running with the particle, so there will be the superposition of these two waves, and the final displacement is given by the summation of displacements by individual waves. And this can be simplified to give this expression, where d omega is very small quantity with respect to omega and dk is very small quantity with respect to k. So in sign terms, d omega and dk can be neglected, and this expression becomes like this, where sine omega t minus kx is original central wave. Here this factor is due to original central wave, and this factor is amplitude of resulting wave, and this is due to the superposition of two waves. This represents that the superposition of these two matter waves give the same wave in the resultant, but the amplitude of the resulting wave is different at different times and different positions, and the maximum amplitude is twice of the amplitude of any of the wave. So this may be called as the wave packet, in which the individual central wave is running, and this is due to the presence of particle. So we can say that particle is somewhere in this wave packet. This is known as wave group, and the group velocity of the wave group is given by the ratio of coefficient of time and coefficient of x, and it is represented by Vg. So group velocity is d omega by dk, and phase velocity is omega by k. Since the particle is somewhere in this wave packet, so the group velocity is equal to the particle velocity. This can be proved also. So these are phase velocity and group velocity, and omega is given by 2 pi mu or 2 pi E by h, where E is total energy of the particle, and k is given by 2 pi by lambda, where lambda is h upon p, or k equal to 2 pi p by h. So we can compute d omega and dk. So Vg becomes d omega over dk equal to dE over dp, and E is the total energy, so kinetic energy plus potential energy. dE over dp will be p by m, where p is momentum of the particle, and this is given by mass of the particle multiplied by velocity of the particle. Mass will be cancelled by this m, so Vg will be equal to particle velocity. So if there is a wave group, then particle may be somewhere in this wave group from this position to this position, and the uncertainty in position of particle will be maximum from this place to this place.